Let's continue in 1.3. I wanted to go over a couple more properties of matrices, 10, 11, and 12. So number 10 is, you can see you have A, B, C are matrices. So A times B times C, A times B times C, same order. Of course, you can't change the order because they're not commutative. We already showed that above. So it's the associative property, right? So you can associate those first or the first two first. So again, the product, you can only do two at a time. So you got to decide which ones to do first. So this implies you do BC first and then multiply by A, or you do AB first and then multiply by C. 11 and 12 is a distributive property of matrices, but notice it is a left and right hand distribution. So 11 is multiplying A on the left side of both B and C, and then 12 is right hand multiplication. So you cannot commute those, right? So it's just the right side multiplication for C. Okay, so 1 through 10, I left them off. It is from that theorem. And I think I added some of my own notes, and I wanted to make sure we covered everything that was in the book. So then number 1, we proved that in the other video, breaking down to components. And then now we're on to the transpose. So let's do some more transpose properties. So definition of transpose, you basically interchange the rows and columns. That's this definition. Wait, well, where'd it go? The definition was before that. You got that. A symmetric matrix is that A equals a transpose. So that'll come into play a bit later, some stuff we do. But the next thing we want to look at are all the properties of, or more of the properties of transpose. So number 2, we proved, this is the last thing I did, and we did the 2 by 2 case to verify. And so next we want to look at, we're going to look at number 4. So before we look at 4, okay, this is where we want to start. First thing I want you to do is try the 2 by 2 case. So on your own, set up matrices, just like we did up here. Use the same ones. They work fine. Okay, so use A, or is it my A? Use A, B, C, D, E, F, G, H, and then work that out with a product. Okay, I have it. I'm not going to work it through. I have it all ready to go. I'm going to paste it in. So pause and try that. So I'll put that down in red here. So try it with a 2 by 2. In general, 2 by 2. Okay, so now we're back. So here it is. Or not. Okay, then I'm going to have to grab it from the other. I thought I had stopped this before. We're going to grab it from here. So here's the 2 by 2 case. I already did it, of course, in my notes. So I had it all ready to go, but I forgot I turned off I forgot I turned it off. So I'll copy it and paste it in here. And so there's the 2 by 2 case. Again, that gives you a way to show things, give you an idea of how to do it in general. This technically would prove it for only a 2 by 2 case. So you want to argue it some way in general. So the one I wrote down here is more, I'm going to write it more of a description. But before I do, I want to look at let's see. I want to look at the vectors and their products. So let's take a look at this. So I wanted to put a little star next to it. I'll refer to this later. If you have a vector A, okay, so we have A as A1 to AN. Then if you looked at a transpose of that, then it's just like you'd think. So this is a 1 by n. The transpose is an n by 1. So it would look like that. So it's you can think of it as a matrix, but it's a vector. It's basically a column vector or a row vector, but it operates kind of like a matrix. So then, if you have B, so A is that, A transpose is that. So suppose you had the same thing for B. So B, actually, let's think of it like this. So that's true what I wrote down, but let's reverse this order. This is how it works for the proof later. So suppose A and B are two column vectors. So we'll start with column vectors, and then their transpose will be a row vector. Suppose A and B are column vectors. And so we'll write it like this instead. I could have led with this, but that's okay. So you have A1 to AN. And then B, let's bring this down over here instead so they can keep it on the same line. And B, another column vector. So B1 to BN. And note that is both of these would be n by 1, n by 1. So you wouldn't be able to multiply A and B with our definition of matrix multiplication. As you see, these are the wrong size. But you can multiply like this. You can if you did A transpose first. Okay, so I'm saying suppose A and B are column vectors of that form, basically. Then A transpose B would be the right form. So you would basically have A1 to AN, which is a 1 by n. And then times B would be the column vector, B1 to BN. And that's the right size. Cleaning up my work a little bit here. Okay, so that is n by 1. So when you do that product, you would get A1, B1 plus, etc., all the way to AN, BN, which technically is a 1 by 1 matrix. But we think of that as just a real number. So that, what is that? That's basically the dot product. Okay, so basically what you're getting then, if you multiply in this format, it is the dot product of just two basic vectors, row vectors essentially. So then if you wrote it like this, so that would be A transpose. So you could do the same thing for B. You could say B transpose A, and you get the same thing. So you get B1 to BN. And then you get, and as you can see, this is the right dimension each. I haven't really defined dimension, but okay. So those end up being the same. Okay. So now we're going to use that concept for the proof of number 4. And I'm going to basically just do a description, essentially. So let's just recopy this. This is just fine. We'll recopy down there. So copy, I'll paste it down here. I'm just going to start a new page. We can just do the next section on new page. So what you get then is this. So I'm going to use this notation. I'm going to say like ijth entry. So that represents the ith column. So you have all these columns and all these rows. So that will be the ith row and the jth column. So the ijth entry of A B transpose is the jith entry in A B, which is, so what you would do, what you get then, you get the jth row of A times the ith column of B. Now think of what that is. That's kind of like what we're doing here for your row and column product. So one of those is times one of those, which is just like AI BJ, but those can commute. Those individual entries may commute. Keep that in mind. Okay, so that equals the ith column of B times the jth row of A. So what we're saying then basically is since this is a form of the dot product, we may commute. You can commute those individual entries. So then you end up getting the ith row of B transpose times the jth column of A transpose. So now, so first we're going to do J row times ith column, but this right here you may commute because they're just, it's like the individual entries of the dot product right there may commute. So if you have Aij, Bij, you can commute that. Because they're individual entries. That's what that statement right here is saying. But then you do the transpose, you get the ith row of B transpose and the jth column of A transpose when you do this. Okay, so if you do that, so that, and I'm saying which is the ijth entry of B transpose A transpose. All right, so and basically they are the same size. So if you have, let's see, I was going to show you back here. Yeah, I didn't write it up over there. So if you have basically this, I think I erased what I was going to show you. Okay, so if you have A, and then it's M by N, and B, let's do N by P, then you can do that product. But to do, so that product is one thing, right? And so that's okay to do. But then when you do B transpose, you get P by N, and then A transpose is N by M. So now you can do that product. So both of those products are defined now and are the same size. So this A B transpose is M by P, but once you do the transpose, it becomes P by M. Same thing here. This product is P by M. So your C is P by M. So they are the same size. Okay, so just whatever you get, right? They're the same size. Since they're the same size and the entries are the same, they are equal. That's basically the argument. So entries are okay. And I was going to finish this here. And so, which is the ith j entry of B transpose. Oh no, I wasn't done yet. A transpose. Okay. Period. Since A B transpose and B transpose A transpose have the same size, they are equal. So it takes a little bit to kind of think through it and what's happening. And it's tough to show something like this in general for any size matrix that has a defined product, right? Of course, A, B have to be defined product. That's why I have you do the 2 by 2 to kind of get a feel for stuff. So that's one way to kind of figure things out, is to reduce it to a smaller size, but don't put in numbers. That could totally mess it up. Okay, let's see. All right, so that was just a short video to finish up 1.3. On to 1.4, which is on solving systems of linear equations, which gets us into the next realm of things we're going to talk about.